Hi there and welcome to this video for Senior Physics, looking at atomic structure as part of the quantum mechanics unit. Now in this video we're going to explore the use of radiation in the exploration of how the atomic structure was discovered. Now there are four main scientists who basically paved the way for our understanding of radiation and the use of radiation in our discovery of the atomic structure. The first was Wilhelm Röntgen, who basically was a German engineer and physicist who explored the material of electromagnetic radiation, which was found to be in the form of X-rays. Now, as a result, he then produced pictures of various objects using this energy, these X-rays, which allowed us to actually look and penetrate deep within the body. And here's a photo of his hand and various objects to see the penetrating effect of the X-rays. The second scientist was a French scientist, Henri Becquerel. He basically worked with radiation. He was exploring the idea of this unknown energy that was emitted from certain types of rocks, later to be known that these rocks actually contained uranium. Now his experiment was that he took a photographic plate, wrapped it in thick black paper, put the rock on top of the black paper, and the result was that he deduced that if he left it in the sun would energize the rock and give off this unknown energy, which left a silhouette on the paper. And an example of this can be seen here, which is an image of his photographic plate. Anyway, one day he was setting up his experiment and it was raining, and as a result he left the photographic plate and black paper, put it in the drawer, put the rock on top and shut the drawer. Anyway, when he developed the plate later, he actually got these silhouettes, as you can see in the image here. Obviously, the sun had no bearing on this energy. There was something inside the rock which actually was giving off this radiation. As a result of this, his surname was utilized to identify form of radiation. So whenever we talk about radiation, the units are always in becquerels. This paved the way for a female scientist who moved from Poland to Paris, where Becquerel was doing his study, and her name was Marie Curie. Now, while she was in Paris, she met Pierre Curie, and between the two of them, they actually isolated the radioactive substance. In this case, the radioactive substance was radium. She also went on to produce polonium, or identify polonium. Now, radium in itself was then utilized in a lot of different substances, makeups, and then it was utilized also in spas. Here's an example of a radium-induced spa, which was all the rage in the time. Marie Curie is famous because basically she was the first woman to gain a Nobel Prize. She was the first woman ever to receive 2 Nobel Prizes, and she was the first woman to become professor at the University of Paris. So these 4 main scientists basically paved the way for the use of radiation. Now the next scientist that we're going to look at was Ernest Rutherford, who utilized the radiation to actually look at the atomic structure. But before we do that, let's just revisit what the various radioactive particles are. So we know that there are 3 main radioactive particles: alpha, beta, and gamma. Now alpha is a big particle coming from the nucleus of the atom, which basically is made up of 2 protons and 2 neutrons. Predominantly it's a helium nucleus. A beta particle is basically an electron. Now the electron comes from the breakdown of the neutron. So you may wonder, how is it that we get electrons coming out of the nucleus? But what actually happens, the unstable neutrons split apart into a proton and a neutron. Gamma is in the form of pure energy. Now if you take the concept of Einstein's theory of relativity equals mc squared, this energy was going to link with mass. Now alpha, obviously just being made up of protons and neutrons, has a positive charge. Beta has a negative charge, and gamma, being pure energy, has no charge at all. You can see that the speed of light here varies, that alpha is a big sluggish particle, so actually goes quite slowly, only 10% the speed of light. The electron is a very, very fast particle, so as a result it moves at 90% the speed of light, and gamma, being pure energy and being part of the electromagnetic spectrum, travels at the speed of light. So let's have a look at its penetrating effects, because this is what's important when we're exploring what's going into the atom. So this simulation here shows our radioactive source on the left-hand side. Now if we look at the alpha particle first, we notice that the alpha particle will actually be stopped by a simple sheet of paper. If we look at a beta particle, the beta particle is able to pass through sheets of paper, but it will be stopped by any metal foil. And then finally, if we look at gamma, gamma will pass through the paper, the metal foil, but it will be stopped by concrete, lead or steel. And this is often why radioactive fuel sources, when they've been used up in a nuclear power station, are stored in concrete bunkers or containers to prevent the radiation actually being emitted. Now, as we said, alpha then is least penetrating, followed by beta, and then finally we've got our gamma particle. Now, gamma was actually identified by the French physicist Paul Villard, and he was the last person to basically add the last little piece to our radiation theory. The particles also have the ability to ionize an atom. Now you can see here that again in this simulation, we've got an atom shown by the rings with the electrons on the outside, and then we've got our ionizing particle. Now notice this is either going to be an alpha or a beta particle. Gamma, being pure energy, has no effect. So how does it ionize? Well, as it moves, it knocks off the electron, and as a result, by knocking off the electron, the ion becomes positively charged. So the speed and motion of the actual radioactive particle will knock off that electron. So alpha is probably our most powerful ionizing particle. This is then followed by beta, and gamma has no or very little effect with respect to knocking off or ionizing the actual atom. With respect to magnetic fields, because of their charges, they are affected by magnetic fields. Remember, if you go back and check out my magnetism iTunes U course, we know that if any charge moves through a magnetic field, it generates its own magnetic field. As a result, this is going to produce a force. The force basically will push against the motion of the particle. So if we look at the alpha particle is positively charged. So if we've got the charge going into the right, we basically use our right-hand slap rule here. And if you remember, we've got to use our fingers. Our fingers basically are the direction of the magnetic field. In this case, it's going into the page. Our thumb is the direction of the alpha particle, and our palm is the force which is applied on that alpha particle. So if we put an alpha particle in a magnetic field, it moves to the left-hand side. Now gamma, being pure energy, has got no charge whatsoever, so as a result, when it passes through the magnetic field, it's unaffected. There is no force that's generated. For beta particles, they are negatively charged, so we use our left-hand rule. Our left-hand slap rule allows us to determine its direction. And what we notice, fingers going in, thumb is going to be the direction. Remember, it's coming from that radioactive source at the bottom, which is stored within the lead container. And what we notice is that the force will be pushed to the right-hand side. So on our photographic plate, we'll get a spot which goes to the right-hand side. Notice the beta is affected or turned more. That's because it's a lighter particle. Alpha requires a lot more force to actually push it through. So let's have a look at Ernest Rutherford. How did he utilize these particles in order to determine the structure of the element? Well, we all know about his famous gold foil experiment. And what he basically did, he got an alpha particle emitter and fired it at very, very thin gold foil, which was only a few micrometers thick. He then had this gold foil stationed inside a detecting screen, which basically had a fluorescent surface. And what he noticed was he was trying to prove J.J. Thomson's theory of the plum pudding idea, that as particles pass through, we've got this this positive particle with this random negativity in the middle. Now remember that alpha particles are positively charged. And what he noticed was that he got this scattering of these alpha particles. Some passed straight through, some were deflected, and some rebounded. And this image basically shows you how the observations occurred. So we've obviously got our first particles going straight through, and as from this he concluded that the atom is predominantly made up of empty space. Then he's got particles which have rebounded. Now when they're rebounded back, obviously there is something which is pushing it. Now the force of repulsion has got to be due to a positive charge, because remember that alpha particles are 2 protons and 2 neutrons. Neutrons have no charge, so the 2 protons gives the alpha particle this heavy positive charge. He also noticed that some particles which were deflected, and you can see this here with the pink highlight, showing that the alpha particles are coming in, they're hitting a substance in the middle and being deflected away. From this, he deduced that the nucleus is dense and it is positively charged, which is causing this repulsion of the positively charged alpha particles. So to recap, the atom is predominantly space, it's got a dense nucleus, which is positively charged. Rutherford was also able to knock out a proton out of this nucleus and identify the proton, and then James Chadwick was able to discover the existence of neutrons which are present in the nucleus. So as a result, we've got this image here to show our new model of the atom, which basically was made up of lots of electrons spinning around the outside with a dense positively charged nucleus made up of protons and neutrons. As a result of this, Ernest Rutherford in 1908 was given the Nobel Prize for his investigations into the disintegration of the elements and the chemistry of radioactive elements and the chemistry of radioactive substances. So check out more resources on my Aussie Physics website. The website is down at the bottom there for you to check out, and I hope you've enjoyed this video. Thanks for watching, and I look forward to you meeting me again. Bye for now.